Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Some people here are very familiar with this work. So Sam did his PhD with Calvin Lin on compiler optimizations by annotating libraries, and since then he's done a number of other interesting things to do with alias analysis and using it for garbage collection. He's worked with Katherine McKinley and other people. And so Sam's going to tell us today about some of the work he's done since his PhD in the last couple of years. So.
Yeah. Well, this is an attempt to kind of tie it all together into a big ball all about static analysis. So most of the research that I've done is really setting out with the goal of expanding the role of compilers in software systems. And really, compilers can be much more than just the sort of, translate your program into machine code. And we've seen a lot of these things sort of come to fruition recently. They can do, error checking, vulnerability detection, program understanding, high-level optimizations, and assist with resource management. And all of these are things that I've kind of dabbled in a little bit. And the way they can do this is by empowering them. So one thing they need is better information. So to do these tasks like error detection and look for security vulnerabilities, they need higher level semantics. So what do programs do? I mean, what does a security vulnerability even mean? And they need expertise. So, what constitutes an error in a program, or what constitutes some high level optimization? The second thing they need is more powerful analysis. A lot of the problems that I showed on the previous slide are much harder than sort of traditional compiler problems, compiler optimizations. In particular, they often need a larger scope of analysis, like looking at an entire program. And they often need sort of deeper analysis, looking deeper at what the program does. And in particular, they need better pointer analysis. And by pointer analysis here, I mean building a compile time model of memory behavior in a program. So pointer analysis is an important problem because it tells the compiler about data structures. And really, programs in some sense are all about data structures, and especially in languages like C and C++ and Java and C#, which is missing from my list there. It's just really critical for languages like that. But of course, it turns out pointer analysis is also a really, really hard problem. So it's undecidable in general, that is, whether two expressions in a program can refer to the same memory location. And so people have built many, many approximations. So there's sort of the near linear analysis developed by Steensgaard, who's here. And then kind of at the top end, there's these like double exponential shape analysis algorithms, very, very detailed. And there's just been dozens and dozens of papers about pointer analysis, and I don't know how many PhD dissertations just about pointer analysis. And I think one very nice paper recently is a survey of pointer analysis by Michael Hind entitled Pointer Analysis, Haven't We Solved This Problem Yet? And I think what's wrong with pointer analysis research is actually captured in this title, and that is the words, this problem. So previous work has really viewed pointer analysis as one problem. And it's kind of a one-size-fits-all view. And the goal is basically produce the best approximation that you can possibly do in some sort of reasonable amount of time. That is, find some fast algorithm. But this brings up a number of pretty serious methodological issues. So what's our metric for best? How do we even know what the best algorithm is? There's this really common metric, points to set sizes, which may or may not predict how good an algorithm works for you. What's the overall benefit of using a more precise algorithm, and is the cost worth that? So our approach is kind of based on the following observation, which is sort of obvious, which is that pointer analysis isn't a standalone task. Its purpose is to provide pointer information to other analyses or other optimizations, which we refer to as the clients. So whether it's error checking or program understanding or whatever it is. And these clients have very, very different needs. So it really doesn't even make sense to evaluate a pointer analysis algorithm independent of what you're going to do with that information. And so we should really stop trying to solve this problem in isolation of those clients. So instead, I think we need to view pointer analysis as a sort of family of problems. And we'll take into account the specific needs of the clients. We'll evaluate the benefit in terms of how it helps that client do its job. And we'll customize algorithmic features specifically for those clients. And hopefully we can kind of do this sort of automatically or semi-automatically. So in this talk, I'm going to present two such customized algorithms. The first is an algorithm for compiler-assisted garbage collection. And this is work I presented at UPSLA last year. And this is a really fast, simple analysis, and it's actually unsound. And in the second part of the talk, I'll talk about an algorithm for error checking, a pointer analysis for supporting error checking. And this analysis automatically adjusts precision to the needs of the error checking problems. All right, so let me start then with compiler-assisted garbage collection. This is work that I did in Java, which, if you're not familiar with this language, it's sort of a C#-like language. And in Java, like many managed languages, modern garbage collectors use multiple garbage collection spaces. So for example, if you have a generational collector, so here's a little picture of the heap here for a generational collector. So you allocate all your new objects in this nursery space. And then the nice thing about this arrangement is that it turns out a lot of objects die young. And that means that I can reclaim some memory very cheaply by collecting just that nursery region. And then I copy the survivors into the mature space, and we call that process promotion, and then you start over allocating new objects in the nursery. So the problem with this arrangement is that longer-lived objects are always copied at least once. And so we looked at the spec JVM benchmarks, and for example, the Java C benchmark, 25% of all the objects will survive the nursery collection. So that's about 47 megabytes out of a total of 185 megabytes. So that's a lot of stuff to be copying, really for no reason. So what's the solution? Skip the nursery. Just allocate those objects that would survive nursery collection directly in the mature space. So that's great, but then we have to predict which objects would survive. And so to do this, we need to look at why objects survive that collection. So one way they can survive is you have some pointer to an object in the nursery, and that object is on the stack, and you're sort of actively using this object. And so it gets promoted because a garbage collection occurs while you're still using the object. But another way that objects can survive is they can be pointed to by objects in the mature space. So remember, we're only collecting the nursery, so we don't know whether those objects in the mature space are dead. And so we assume conservatively that pointers from the mature space into the nursery are potentially live pointers. And so those objects survive. And actually, it turns out that most objects survive because they're connected to older objects. So you're building some big data structure, and you allocate new parts, and you attach those objects. Yeah? Well, eventually, when the mature space is full, you'll do a full heap collection and collect the mature space. That's an expensive operation, though, so you want to do that infrequently. Yeah, that's a good question. So, for example, so in Java C, we had a lot of objects surviving nursery collection. It turns out only 10% of them are promoted because they're pointed to by variables on the stack. And 90% are promoted because they're pointed to by older objects that are in the mature space. So the pointers between objects are predicting the survival of those objects. So when I create a new object and I point to it from the mature space, that object will be promoted. So really what I should have done is co-located that new object with the source of that pointer. So what I'd like to do is anticipate the existence of this pointer and allocate that pointer target in the same space as the source, like that. So now that pointer helped me bypass that promotion. So we built a system to do this automatically, and we call this dynamic object co-location. Yeah? So the nursery, there's two reasons. Sure. No, that's no problem at all. No. So the nursery often, okay, so the nursery is smaller than the mature space, for one. And, what's that? God, that's a good question. That's a whole philosophical sizing the nursery. Maybe 25% of the heap? Sure. I think it's kind of really a black art. I mean, there's also variable size nurseries that, the key feature though of the nursery is that it contains newly allocated objects. And there's this thing called the generational hypothesis, which says that a lot of objects die young.
No, it's not different. There's no qualitative difference in how it's implemented.
No. It's sort of the demographics too. The survival rate is low in the nursery, and the cost of collecting the nursery is proportional to the number of objects that survive. Yeah. Okay. Okay, so we implemented this system. The key is it's a cooperative approach, so there's a runtime component and a compile time component. So the runtime component consists of a new allocation routine that works a lot like regular new or alloc or malloc, except that it takes an extra argument, which is an object reference, and we call this reference the co-locator. And at runtime, what coalloc does is it looks at the co-locator, determines what space it's in, and allocates space for the new object in whatever space that's the co-locator's in. And then the compile time side is a static analysis, and what it does is it determines at a given allocation site if the new object will be the target of some pointer, that is, anticipating the existence of connectivity. And then at the allocation site, pass the source of the pointer as the co-locator. So you can see that together, these two things will cause connected objects, maybe even large data structures, to be allocated together in the same space.
Okay, you need a compile time thing because you have to know when you're doing the allocation, you haven't set up the pointers to point to it yet.
You have to see the future.
You have to see the future about who's next
Right.
am I going to be or whatever.
Right. I mean, this is really, in some ways, I think the essence of what runtime and compile time things are good at, right? The runtime system sees exactly what's happened in the past, which is where objects ended up. And the compile time side has some approximation of the future. That is, how will things be connected? So here's kind of a really simple example of what this thing is trying to do. So here's a method called simple, which takes an argument P of type A. It creates a new B object, and then it points to that new B object with the A. And because of the existence of that pointer, we know that the new B object will live at least as long as the A object. And I got a little asterisk on here, which I'll come back to. I'm sure you can imagine what the issues are there. So what we'd like to do is co-locate that new B with the A object. And so to do that, we replace the new with a call to coalloc, and we pass the argument P in. And then coalloc will look at that object, figure out what to do. And the key is that the runtime value of P determines the behavior. We're not making a static decision about where to put the new B. So if the A that's passed in at any given call of this routine exists in the mature space, the new B will also go in the mature space. But note that if the A passed in is in the nursery, then the new B will go in the nursery. And that's kind of the behavior you would expect, the behavior you want. And then the asterisk here, obviously, unless that field is overwritten by some other value. And I'll talk about how we deal with that problem. Here's a slightly more complex example. So again, we have an input P of type A. We create a new B object, and we also create a new C object. We point to B with C, and we point to C with A. Now, what I'd like to do is I'd like to have C be the co-locator for B, because it's the object that immediately points to it. But it can't, because it doesn't exist when B is created. So there's a problem. The order in which we create things and the order in which we connect things can be a problem. The solution is we can just use P as the co-locator for both. The reason is the connectivity between the objects is transitive, and therefore this property of survival is also transitive across those links. And this observation can also greatly simplifies the algorithm for finding and instrumenting the code. So there's the result. We just pass P to both of those calls. So here's what we're trying to do. So to find a collocator, first of all, we'll always use the formal parameters as collocators. The one reason for that is they're more likely to refer to older objects. And then the second is, as I showed on the previous slide, the order of the creation and connection of objects within a method doesn't matter. So we don't have to worry about who got created first. And our goal is, for each allocation site, will the object created at that site end up connected either directly or through some chain of pointers to the formal parameters of that method. And we'll do this using a customized pointer analysis. So we'll build a graph, a connectivity graph of what's going on in the method, and use that to discover collocators. Yeah, like a factory method. So we have, I'll touch on this really briefly, but we have an interprocedural analysis as well. So we can, we have a way to handle things like factories and right. We treat a factory method as if it's an allocation, pass in an extra hidden parameter, and then use that inside. And that can actually go down many levels too. It's a good question.
So Sam, so the potential problem I would see here is that if your pointer analysis is really conservative, and you think that everything's connected to everything, you will start co-locating all these objects with formulas that are sitting in the mature space and lose the opportunity to allocate them in the nursery.
Right. So you can. I'm going to get to that in like 2 slides. So let me first show you the algorithm, and this is one of the things here that's nice about this. I can basically show you the whole algorithm on 1 slide. So we basically do this one method at a time, and so here's some method foo that takes 2 arguments. We build a points to graph, which has a node for each incoming parameter and a node for each allocation site. And so let's say, so there are the parameters, and then there's some number of allocation sites in the method. And then edges between these nodes represent possible points to relationships. So sort of the traditional pointer analysis representation. We visit each instruction in the internal representation. And then the essence of it is we just add edges each time we see a put field or an array store. So this, again, this is Java. So these are the sort of two ways that objects can get connected. So you end up with some graph showing how objects might be connected. And then you find co-locators by basically following the graph from the parameters to the allocation sites. So for example, P is probably a good co-locator for that new E object because it will end up connected to that parameter. And that's basically it. And then instrument the program with those values.
So these nodes are not, this is like a type-based graph. These nodes are for a whole class.
These...
One node for A, for type A, and one...
No. These are for allocation sites.
Allocation site.
So you take a method, and for each new that you see, you create a node. I know I've shown it here sort of as types. You could certainly have, a whole bunch of new D objects corresponding to different static sites in the program. Yeah. Yeah. Mm-hmm. Uh-huh. Oh, I'm just showing one example. P would be the co-locator for C, E, and G. Yeah.
So you don't do any like analysis that actually can be.
No. But I'll show you a detail about that. So the algorithm has a bunch of interesting features which all come from the following observation. And that is that this decision, whether or not to allocate in the nursery or the mature space, doesn't affect the correctness of the program. So the analysis we're using doesn't have to be sound. That is, it may miss possible pointer relationships between objects. And so it would probably be unsuitable for something like optimizations, where correctness is sort of at stake. But this lets us do a lot of interesting things with the algorithm. So for one, we can make the algorithm much, much simpler. So it's a one-pass algorithm. There's no fixed point computation or anything. And that was kind of an arbitrary decision, but it's just so easy to implement. And then the other thing is we don't make any of the sort of typical conservative assumptions. So as you saw in the previous slide, we assume parameters don't ever alias each other. And we don't have to make that assumption because it doesn't matter. The second thing is we don't have to make the so-called closed world assumption. So a lot of static analysis for languages like Java, and it's probably true for C# too, have to deal with things like class loading and reflection and native methods. And so for a sound analysis, either you have to do something very specialized for those language features, or you sort of have to punt and say, you know what, this only works if I can see the whole program. Our analysis doesn't have to be sound, so it'll work with these features. Now, it won't understand what those features do, but it won't break the program. In addition, we can specifically ignore some pointer connections in the graph. And again, we can do this because of unsoundness. And we'll use this specifically to prune out pointers which might otherwise cause, let's say, the mature space to be filled up with garbage, with objects that don't belong there. So for example, as you saw before, I had that asterisk. You know, what happens if this field is overwritten with some other value? Well, if we can detect that a field is being overwritten, we'll just leave it out. So we developed a set of heuristics, and I'm not sure if these are complete, but they work very well for the programs that we've looked at. And it's basically that there are these some connections that should not cause colocation. And some examples include overwriting a field. There's also a conditional store. So if you create an object and then only on some branches do you store that object, it's probably safest not to colocate that because you don't know the frequency of the true or false branches. And so the safe thing to do is not to do colocation there. And if you make a lot of mistakes, and in the paper we kind of showed what happens if you turn off these heuristics, you get, you can end up with basically all the objects in the mature space if you're not careful. And we'll just prune these connections right out of the graph, and again, won't affect correctness. Mm-hmm. Just by the normal collection process. Well, that's done by the normal runtime system. The way the That's right. That's right. So the other feature, which I won't go into a lot of detail on, is it does have an interprocedural analysis. So when we analyze a method, yeah. Nursery, yeah. Yeah, yeah. Yeah, I mean that's sort of how the normal garbage collector would work, independent. There is a You're bringing up a good point about the algorithm, though, which is that it does require a kind of a warm-up, which is you have to get some of the kind of top-level objects into the mature space. And then, so for example, in the first couple of collections, the algorithm does very little. But then as data structures survive collection and are being constructed more in the mature space, the algorithm starts to draw more of the objects into the mature space. But it does kind of have a warm-up period where initially the algorithm isn't really doing anything special. Again, that will happen just naturally with the... Yeah. Yeah, that's right. Yeah. Yeah, that might be possible. Yeah, we haven't really looked into that.
And that would apply to again.
It would. One way.
Trade-off because you maintain that table of the time.
Well, one thing we had looked at, but have not really had a chance to implement, is actually putting those co-located objects in an entirely separate space. That's just dedicated to data structures being constructed because of co-location. And then you could treat that whole space as kind of a special case.
Yeah, that you don't collect except like one shot to collect.
Exactly, right.
Yeah, it seems like you have a problem that when you make a decision to promote somebody, and it's a mistake, basically, it sort of propagates itself.
Yeah.
So it'd be interesting to see your error rate over time. Basically, how often you act incorrectly promote somebody as a function of the execution time of the program. Because for long-running programs, you can see how it degenerates everybody being allocated in the first place.
Yeah.
Because these things propagate. So one thing to think about with the algorithm is how to back off of errors. I mean, in some sense, once you make a mistake, you have no way to recover from it.
Yeah.
And so every time now you see that. Right, exactly. Well, even there, you have to remember per object whether it was brought there because of one of these pointer things versus it just got there.
There's one of Catherine's students, Maria Jump, had this system for object sampling where you randomly sample some small fraction of objects and track precisely their survival rate according to the allocation site. And that kind of thing could be used to sort of maybe have some form of accountability at runtime like shut down some allocation site if it's just consistently making the wrong decisions. But again, it does require a major collection to even find out if you're making a mistake. So let's see. So interprocedural analysis, this actually turns out to be pretty important. So for factory methods, as was mentioned earlier, and also sort of connector methods. That is, you have a list class and you have an add method. And that add method creates the connection between the objects. If you can't see what's going on in that method, you won't see that connection. And so we compute very, very simple summaries about how objects might be connected. And again, because of the, without the soundness constraint, if we have summaries, great. If we don't, well, too bad, So we implemented this system in the JICE RVM research Java virtual machine. We looked at two different generational collectors, one with a copying older space and one with a mark sweep older space. And what we did for this work is we compiled all the methods ahead of time to sort of get, see what the maximum benefit. And we looked obviously at the spec JVM 98 benchmarks and then also at the JBB benchmark. And the goal here is really to reduce the nursery promotion and see how that affects garbage collection time. At the same time, though, we have to avoid filling up the mature space with garbage. So here's kind of the central result of the work. So what I'm showing you here is, so across the top are the different benchmarks. So there's a pair of bars for each benchmark here. And then on the y-axis, I'm showing bytes of allocation that end up in the mature space. And that could either be by promotion or by directly allocating objects there. And I've normalized it to the behavior of the base unmodified collector. So for example, for javac, you can see 47 megabytes of memory end up being promoted from the nursery into the mature space. And then the second bar is with colocation. And so this shows the reduction in the amount of memory that has to be promoted from the nursery. Yeah.
Okay. This reduction is because what the objects you put in the mature space.
That's right. So that's this. Okay? So now what I've added here is this sort of yellowy bar is the amount of memory allocated directly in the mature space as a result of colocation. So in the ideal situation for colocation, the sum of the blue bar and the yellow bar should equal more or less exactly what would otherwise have been promoted. That is, it's deciding exactly the right things to put in the mature space. And it's not always exactly true, but it's generally doing pretty well. For most programs, we're only off by maybe 5 or 10%. For programs like Jess, so it's not doing a great job on Jess, but if you look at these numbers in absolute terms, 2 megabytes versus 2.7 is not likely to make much of a difference. JBB, it's very aggressive. So this, using colocation on JBB, if you give it a lot of memory, so it has a big mature space, then colocation can really help it run faster. But in a tight heap, colocation is still a little bit overly aggressive, and that will incur extra full heap collections. I think really one of our best results is javac, which is one of the more realistic programs in the benchmark suite. So, and here we're significantly reducing by about 65% the amount of nursery promotion with very, very little overhead. And so this graph is showing the effect on javac on garbage collection time. So here, along the x-axis, I'm showing a bunch of different heap sizes. And then on the y-axis, I'm showing garbage collection time. I guess the units aren't really critical there. The red and yellow lines are the baseline system, and the blue lines are the same systems with colocation turned on. And so, for these kinds of kind of moderate and large heap sizes, the reduction in GC time is pretty significant. So it's about proportional to the amount of savings in promotion. And yeah.
So, did you compare against pretenuring?
We didn't compare directly against pretenuring. We looked at the previous papers, and in terms of the amount of stuff, we're doing quite a bit better in terms of the amount. We didn't measure the runtime. That is, we didn't re-implement pretenuring. We did note, however, that some of the most important allocation sites in programs like Java-C are in the Java libraries. And it's almost impossible to make a static decision for a lot of those allocation sites.
My recollection is that actually Java-C was one of the applications that pretenuring did pretty well with.
I think either the number 1 or number 2 allocation site in Java-C, though, is like a 35-65 split as to whether objects survive or don't survive.
But if you use the call stack, then it's
Yeah, we didn't look at that. If you used some call stack information, you might be able to do that. I mean, that's in effect what colocation is doing, right? By passing objects down through the call stack, you're in essence providing that information.
That's right. It's another way
To provide context.
to call it.
Exactly. It's sort of more readily available, though,
Yeah.
because those pointers are already there.
So is that 35, 65 split actually for the 4 megabytes in Sweden?
The problem is there are things like vectors. So, if the system's allocating a vector, can you decide for all vectors whether they're going to be long-lived or short-lived? It's very hard to do that. So that's where the 35-65 split is. Some vectors are just being used for some throwaway purpose. Others are some component of a long-lived data structure. So what you really want is vector to sort of be parameterized by what's it going to be used for. And that's what we end up doing. And then this is sort of the result averaged over all of the benchmarks. So, it's sort of in the 15 to 30% reduction in collection time over all the benchmarks. Okay, whew. Halfway through. I don't know where I am in time.
Yeah, I think if you go through take less time for the second part, you'll be better off.
Okay. I'll try to do this quickly.
Slow down.
I was actually hoping to spend more time on this, but
I know.
oh well. Too easy to get sucked into interesting problems. Okay, so this part of the talk, I'm going to talk about a pointer analysis algorithm for error checking. And this was developed in the context of my dissertation work, which was analyzing and optimizing C programs. And so here's sort of the motivation for this piece of work. So you need pointer analysis to do good error detection. But a lot of times, pointer analysis is sort of this thing that's kind of like slapped onto a system after the fact. Like you come up with this really clever algorithm for error detection, and then you realize, man, this thing's not going to work unless I have some sort of model of pointers in the program. So, here's sort of the typical situation. So you have your client, your error detector, and it might be a data flow or a type system or model checking or who knows. And then you choose some pointer analysis algorithm. Here's some like kind of common features that people choose for pointer analysis. So kind of at the sort of faster, less precise end, you might have context and flow insensitive algorithms. You might think you need flow sensitivity, or maybe you figure, I need the whole kitchen sink, so it's context sensitive, flow sensitive. The problem with this approach is you're sort of deciding a priori what's needed. So here's kind of a real life scenario that I did using my error checking system. And in this scenario, I was looking for security vulnerabilities in this program called Black Hole, which is a mail filter with the typical lovely naming for Unix programs. So here's what I did. I started out with the context-insensitive, flow-insensitive pointer analysis. Or I actually applied that precision policy to both the pointer analyzer and the error detector. And the error checker comes back really fast, and it tells me that there's 85 potential errors in this program. I'm a little suspicious of this because, this is a program that's been out there for a while. I don't think there's 85 errors in it. So I crank up the precision on my analysis. So the main benefit there is that it runs 25 times slower and still produces the exact same 85 potential errors. So then I figure, all right, I'll just go for the gusto on this thing, and now my error checker just runs out of memory, just blows up. Okay, so what do I do? So now I start combing through these 85 error reports, and I notice that they all have one thing in common: a particular string processing routine. And kind of just on a hunch, I clone this procedure manually. I just cut, copy, and paste. And then I rerun using the cheapest analysis. And it turns out that all 85 of these things are false positives, and they all go away. Yeah?
So you used 3 possible combinations of CSS.
Yeah.
But you didn't use the 4th.
Uh,
You have fixed it from, and actually use the cheaper ones.
yeah, that's true.
Well,
That's true. I did have access to that, although at the time I did these experiments, we didn't have algorithms like the the BDD-based algorithms that are available now. I mean, that might be. I mean, who knows? I think there are definitely cases where flow sensitivity is necessary, and it's not clear how to incorporate. Here it was, right? So yeah, I can have an armada of algorithms that I just throw at this thing and see what happens.
It's just interesting why you do that particular report.
It was capable. The system is capable of doing that, and I'll show you later graphs where I did actually look at context-sensitive, flow-insensitive. But still, in our implementation, it was still very expensive to do that. We basically did it by cloning, and then,
But there's a way to implement it.
yeah, now there is. That's true. Yeah. So, but really, the point is, why do that when really I only need one procedure to be analyzed context-sensitively? And so the question is, can we automate that process? So the problem here is created by this very extreme kind of cost-benefit trade-off for pointer analysis. And the precision choices are very, very coarse. That is, it's all kind of all flow-sensitive or all not flow-sensitive. And you kind of have to make this choice ahead of time. I mean, you could implement lots of new algorithms. I could add a new algorithm, but that's a huge effort. And I have to make it before I even know whether that will help me. So our solution is a mixed precision analysis. And the goal here is to use high precision only where it's needed in the program. And everywhere else, we'll just use really cheap analysis. And the key is we'll let the needs of the client, that is the error checking problem that we're actually working on, dictate where that precision is necessary. So here's how the algorithm works. So we start out with the fast, cheap analysis. We monitor during that analysis how information gets lost due to this imprecision. And we put that into this dependence graph, which I'll describe later. And then we create a customized precision policy and rerun the analysis with that customized policy. And that might specify, for example, make this one procedure context sensitive. And then hopefully that yields a better result. So first, let me describe a little bit about the sort of core analysis framework. It's an iterative data flow analysis framework, and it solves both the pointer analysis and the client analysis together. And that allows it to kind of monitor their interaction. And then second, it supports fine-grained precision policies. That is, we can choose context sensitivity on a per procedure basis, and we can choose flow sensitivity on a per memory location or per variable basis. So we can use that to compose a very customized policy. So now let me tell you about a little bit about what's going on in the monitor and adapter parts of this. So to understand this, you sort of have to look at why false positives happen in the first place in systems like this. So let me describe to you first one of the security vulnerabilities that we actually looked for in our experiments. So if you take a look at this code, this is sort of Unix system programming code. It reads some data from a socket and then calls exec on that data that it read. And this is like your system administrator's like worst nightmare. Basically, read some data off the internet and execute that program on your computer. So that's a pretty major security hole. So here's a program, and I'm showing you like a call graph here. So you've got main and you've got calls to socket and read and exec. And let's say that there's a path through this program that shows this this vulnerability. So socket, read, and exec. But then let's say there's a totally different path through the program. So here, let's say we read from standard input and we'll say, hey, if you're sitting at the console, then you can type commands and exec them. Let's say that's not an error. And the problem is, what happens when I analyze this program, especially with context insensitivity? These two paths merge at this common reused function. And it's data flow analysis, so I grab my handy lattice here. So I have to merge the error and no error paths, and I get this kind of yucky maybe error color. And then that propagates back to both of the calls to exec. So now instead of one error, now I've got two possible errors. Okay, so here's what we do about that. So the monitor process runs alongside the main analysis, and it monitors, it's looking for that situation where I had these two precise lattice values, and then when I merged them together, I ended up with a sort of maybe value. And we refer to these as polluting assignments. And then in addition, it sort of tracks, well, where does this imprecise information go after that? And we refer to those as complicit assignments. And it assembles those into a dependence graph. And it does that for both the pointer analysis and for the client error detection. And here's basically how the dependence graph works. So if you've got context insensitivity or flow insensitivity, you can create this maybe value in two different ways. So, for example, in context insensitivity, if I call the procedure foo with a non-error value and I call it with an error value, then the parameter will get assigned this maybe value. Or with flow insensitivity, if I have multiple assignments to a variable, green and red, then eventually that variable will end up with the yellow value. So what we do when we detect polluting assignments, we create a node in our graph, and we basically annotate that node with what you need to do to fix that value. So for example, in the context insensitive case, if I need the variable parameter to be more precise, what I need to do is make foo context sensitive. And then similarly for the variable x, make x flow sensitive. And then for these, yes?
How do you decide whether you need more precision at that?
I haven't made that decision. All I'm doing is recording.
If you don't make that decision, what you're doing amounts to just let's be as precise as
That's exactly right. All I'm doing here is recording where imprecision happens. I don't know yet if it's important.
I wonder technically, if you have to record enough information to exactly decide where precision was lost in a merge-based data flow analysis, are you going to have to generate a fully precise analysis?
No.
It's
It's much smaller.
oriented.
No. This information is much cruder.
Okay.
Yeah.
It's literally just the points where things come together and then, okay, you know,
And it's a
very
node.
serious.
There's only a node for each, basically for each variable. So it's fairly small.
In fact, it's a linear, it's just the size of the control flow potentially. Right?
That's right. So, and then for these assignments, these complicit assignments that just convey a yellow value from one variable to another, we create an edge between the two nodes. And notice that the edge is backwards along the assignment. That is, from x back to y. And you can see that's going to eventually let us follow from a possible error back to the source of the imprecision. And there's actually another way that polluting assignments can occur, and that's indirect assignments through a pointer. So if I have an expression like x equals star pointer, and the result is x's yellow or a maybe value, that can actually happen in two ways. One is that the pointer points to some variable whose value is already this maybe polluted value. And we just treat that like a complicit assignment. In a sense, it's just saying x equals y. And so that isn't treated in any special way. But the other way that can happen is the pointer can have an ambiguous value, where the targets don't. So I could have a pointer that might have two possible values, but those targets have precise values. In this case, I'm sort of going to hold the pointer accountable for the problem. That is, in order to make x more precise, what I need to do is make the pointer itself more precise. And that's how the client and the pointer analysis actually sort of interact. So at the end of the first run, I have this dependence graph. And each node is basically a memory location or a variable. And keep in mind here that the edges are sort of flowing backwards in the execution. So then I start with the arguments passed into the exec-L. That is, the values that actually trigger these maybe errors. And then I just follow all the edges through that graph. And along the way, I collect up all the diagnoses that are annotating those nodes, and I assemble that. And that becomes my precision policy for the next run. And the good news here is that this is often a very, very small subset of all the imprecision that is in the program. So here's kind of the whole system in action. This is sort of my PowerPoint homage. So here was our original problem. We had to merge these two paths. So we detect the fact that that one procedure probably needs to be context sensitive by detecting that polluting assignment. Then we apply that fix, which effectively clones those procedures. Now when we reanalyze, we keep those two paths independent. Now we have exactly one true error. So here's the experiments we ran. We downloaded 18 real C programs, open source programs, totally unmodified source. Many of them are system tools, so where security would be an issue. We came up with 5 type state error checking problems. Some of them had been used in previous research, and a couple we just cooked up on our own. And they represent, non-trivial program properties, and they actually do stress the pointer analyzer. And we compared our client-driven algorithm to several commonly used fixed precision algorithms. And first, our sort of first goal is to reduce the number of errors reported. And since all these analyses are conservative, they're all sound, fewer errors is always better. And then second, when two algorithms produce the same number of errors, then clearly we want the faster of those two. And so here's the big results graph. So along the x-axis here are all the different programs we looked at. The y-axis is analysis time normalized to the fastest analysis algorithm, and that's the context insensitive, flow insensitive. And It's a log scale, so it gets expensive really fast. And what I'm showing you here is the number of errors reported by that analysis mode on that program. And this is for this remote access vulnerability, the one I showed you, the read exec vulnerability. So here's what happens when you add flow sensitivity to the analysis. So you can see now that the cost of the analysis is in the sort of 5 to 20 times, 25 times more expensive. And for some programs it helps. So, you know, for this FTP daemon, adding flow sensitivity got rid of a whole bunch of false positives. But in many cases it actually doesn't help at all. And you can see here's black hole in the middle with you know, quite a bit more expensive and no real benefit. Here's context sensitive, flow insensitive. And I guess I should say that because of our implementation, this doesn't even finish running on a lot of programs. That might not be true with some of the more recent implementations of pointer analysis. But again, it's not clear to me either how to make like the error detection analysis fully context sensitive in addition to the pointer analysis. So I'm not exactly sure how those newer algorithms would be adapted. And then here, of course, is the sort of full precision mode, which again may or may not help. It takes so long to run and often runs out of memory. So here's kind of the punchline. So here's the client-driven algorithm. It sort of sits somewhere in between the context-insensitive, flow-insensitive algorithm and the flow-sensitive algorithm. An interesting thing to note here is that if there are no errors, then we don't do any extra work, right? If the first pass of the algorithm detects no errors, you're done. There's nothing else to do. So that's nice. There's no, there's no overhead of running some very complicated algorithm. And here is the results for black hole. So you can see that with the proper context sensitivity, there are no vulnerabilities in the black hole program. So in conclusion, I think it's really important to start looking at different algorithms for different clients and to kind of stop looking for that one perfect pointer analysis algorithm that will do everything. And one of the ways to do that is to sort of challenge the assumptions that that are built into a lot of the research, like soundness. Is soundness really needed for our applications? Is precision a fixed property of the analysis? And then my current research has been pursuing more of this sort of compiler runtime cooperation. I think this is a really interesting area as well, sort of because they're very complementary systems. I think someone said, I wish I'd thought of this quote myself, but the runtime system has an approximation of the past, and static analysis has an approximation of the future. And so together they have a lot of powerful information. That's it.
So in your client-driven analysis, would it be beneficial if you stuff at the community graph also option to identify that suspicious articles that start from there and construct
Not entirely sure I understand the question. I mean, I think part of the reason you need the dependence graph is because you sort of...
So you kind of construct this whole graph, and then for every error check for this, you go through the exercise
Yeah.
of, now when you go back all the way, and you stop at the point.
We pretty much go back all the way. I mean, as long as we're finding the maybe values or the may values, we keep going. We do all of the errors at the same time. So if it finds 85 errors, then we'll do 85 different traces through the dependence graph. Collect all of that together.
So there's only one
That's right.
iteration.
There's only one iteration. We actually looked at kind of multiple iterations, and it turns out not to help.
No, in fact, the guys who do multiple iteration like Slam, they have scratched their head for years to try to figure out how to do it in one shot.
Well,
They have the problem that they only see one trace at a time, so they can't do what they think.
right.
But they would actually, from their experience, prefer to do it your way.
Well, what we did, I mean, we experimented with that. What we found is it was much better to be overly aggressive about adding more precision.
Even though that will slow down, you're getting the benefit of getting hold.
That's right.
One thing one problem I can see is that when you deal with very large components, that's the part that you want to analyze. You can't really afford to use the full data structure, sensitiveness, and all that.
Yeah.
Then you have to do some sort of measuring.
Yeah. Right. Well, certainly, at least one encouraging thing are some of the advances in context-sensitive analysis, which might make it easier to use more context sensitivity. I think that in some sense, if the initial pass of the analysis tells you that you need a lot of context sensitivity, then you do need it. And, then it's just a matter of figuring out how am I going to do that efficiently.
I mean,
Sorry. One thing I think that would be very useful is that when you look at the dependency graph, maybe another flow is really unrelated to the topic. So that's relevant to really related to that geography that but otherwise you can still work with
so I want to go backward from the error point is getting in that effect already.
That's the goal. Yeah, I mean, the goal of the dependence graph is really to only visit those
Try to be
things.
as demand-driven as you can.
Yeah. Now one area that could be improved is that the dependence graph the dependence graph itself is not flow sensitive. That is, I may follow multiple outward arcs from a variable, not knowing whether those assignments are really important.
See, where these questions are coming from is that, so we've done some work with ESP that actually Jason's done about, we construct a dependence graph too, but that is an actual representation of our path-sensitive, context-sensitive
Right.
analysis to find bugs.
Right.
And we use that structure when we get an error that we think is a false positive. We walk that structure backwards to find places where we merge symbolic information.
Yeah.
And then we teach the symbolic evaluator that don't merge that information, then we rerun.
Right.
So that's like our iterative refinement.
Right.
We're doing that. And so I guess there our dependence graph is much more accurate because it came from the actual full-blown analysis. But
Right.
we did this whole full-blown analysis up front.
Right.
And it's really, I'm really curious about how this relates to all the stuff we do in ESP. Because on the one hand, I would say everything I think about ESP, we picked the criteria up front for how to tune the analysis. We said that you give us a property and all the context sensitivity and flow sensitivity and path sensitivity and everything that you need will come out automatically from the fact that you're tracing that property. It's just like you've got these data flow facts that matter and you just use a standard RHS-like thing and you automatically get just the context sensitivity that is differentiates those data flow facts and not the rest of it or just the. So yeah, there's some, I can't claim to understand it all, but it would be curious, I guess, for us to think about what we're missing from here that we could incorporate better ourselves.
Well, here's one interesting feature that I've noticed happens in this algorithm. And that is that the algorithm detects the merging of flow values before the system has converged. And so sometimes it detects it detects information that's often not available in the final solution of the analysis problem. For example, a typical problem is when a flow value enters a loop, and then that flow value will propagate through the loop until, let's say, all the variables assigned, all the variables that have control dependence through that loop will all have the same flow value. Once you have that solution, you can't reconstruct where that flow value initially entered the loop. But one of the things that happens in this analysis is when that flow value first enters the loop and causes it to become a may value, you actually remember it at that point. I don't remember how, I'm not exactly sure how important that feature is, but it is actually seeing the data flow analysis before it's converged. And I don't, yeah.
Some of the maybes are introduced because we call functions we don't have access to source code. So you can't traverse them to figure out what's going on.
Right.
Have you looked at determining what kind of annotation you can put on such functions that would allow the model to work correctly?
Yeah. In fact, well, that's almost like a straight man question for me, because really my dissertation work was annotating library interfaces so that compilers and analysis tools can get something out of the library calls without having the source code. And so the tool that was used to do this experiment, really all of the libraries that are used by these programs have been annotated with data flow information so that there are, in fact, no procedures that have to be handled conservatively. Yeah.
If there's no more questions, let's thank the speaker. Thank you, Sam.
Thank you.